We spent the first session telling you what are the stakes. What are we, let's say, what the fight is for. The fight is about privacy. The fight is also about getting cryptography, the things that we cryptographers build for privacy or transparency or everything, to be actually adopted. And sometimes the hoops are on fire and very small. So this next session, we are going to dig a little bit deeper. We are going to talk about what zero knowledge is, because we told you about it as a black box. So the first talk here is from Marek, our great friend in the chess project that also is supporting this event. So Marek will tell you about constructions and a bit more.
Thank you very much. First of all, I would like to tell you that I'm not working in this field, but I would like to give you my point of view on the zero knowledge proof, how I understand zero knowledge proof. So I'm going here against what Dan at the beginning said, that zero knowledge proof is in fact hard, and I would like to give you a simple understanding or rough understanding of what are the ideas behind zero knowledge proof systems, and what are the limitations, maybe trade-offs. And definitely I won't go into details, but I will try to cover the ideas and big picture, and I will try to explain it in more digestible form based on something you most likely probably know, and I will use a mental model based on digital signatures. Okay, so let's start from the beginning, and what zero knowledge proof system offers. First of all, there are three things. They offer privacy, which means that you can hide some data, private data, or some secrets, passwords, whatever. And the second very important property is that provide verifiability, which means that anyone can verify some claim related to given data, like private or public data. And even more important is the third property, succinctness, which means that to verify the claim, the claim can be verified very easily, very efficiently. The claim is small, so this is especially used in production, current production, where succinctness and verifiability is used in maybe rollups, and Jano will be, I think, talk more about them, right? First of all, not all systems, not all applications use all these three properties. Rollups use only succinctness and verifiability, but most of the systems rely on all these three properties, where they provide some claim about some private data, and anyone can verify this claim very efficiently. It should be noted here that the zero knowledge proof systems are not widely adopted, and the reason for that is that they are very or quite expensive with respect to standard cryptography we are using these days. And for most of the cases, the standard cryptography is sufficient. Okay, so the use of zero knowledge proof must be justified by the really required all these three typically properties. Okay, typically for practice, two of them or some of them can be covered by classical cryptography, like digital signatures, for instance. Okay, so what zero knowledge proofs provide, or which claim can we prove here? The first one is the knowledge of something, of some secret, of some private data, like I know some password. A property of some data, that some age is bigger than some threshold. And in general, we can say that some computation over private or public data, and I will talk mostly about the processing of private data, okay? So in general, we have here some private data as an input to some program or some rules we want to verify, and the result is some public claim. And all these things are put together as a proof, and this proof can be verified by anyone, as I mentioned, very efficiently. Proof is designed or is created to be quite small, so methods in zero-knowledge proof systems try to condense or compress somehow the entire computation or verification so that proof can be verified very easily. As an example, we can see here that birth date is compared to some threshold, which can be seen also as some very small, tiny program consisting of one comparison only. But as you will see later, even small and tiny operation can be, or when transformed into zero-knowledge proof ecosystem, became the more complex algorithm. Okay, so every single operation has its cost, and the principle of zero-knowledge proof optimization is to decrease the cost of the verification or to minimize the size of the proof. Okay, first of all, the entire program, or let's say this way, zero-knowledge proof system is just about to have some program which is applied to some data, and the result is public output. Okay, and if the proof is verified or valid, that means only that the input data really was processed correctly, so we validated this way the correctness of the result with respect to input. Okay, it does not mean that the input really corresponds to reality. So if issuer inputs some input data to the zero-knowledge proof system and the result is valid proof, that does not mean that this has something to do with reality. So once again, valid proof does not mean that the real world claim is correct. In general, any program we are going to validate it using zero-knowledge proof system must be transformed into specific form. And this form is just relation of some intermediate variables used by the program or some additional variables. As you will see, we will add some additional variables to express some more complex functions. And it may happen that some of the constraints are forgotten by the developer of the system. So during the transformation of the standard program into the corresponding form in the zero-knowledge proof systems, it may happen that some of the constraints are forgotten or not written there, which means that in fact the different claim was provided during by the given proof. So, and this will need some expensive audits and crypto and software expertise. So this will definitely increase some cost with respect to standard programming, right? So this is zero-knowledge proof in general is not only is also the engineering problem. So how to transform given program to program for zero-knowledge proof systems. Okay, so now the key aspect of zero-knowledge proof system is that there is a big asymmetry between prover and verifier. So there are two roles: one who claims something, who uses the program, applies it to some secret data, and the result is produced proof, which is compact cryptographic object, let's say. And the verifier who verifies it using some cryptographic operations like exponentiations or some operations in elliptical systems and so on. So Here, the asymmetry, in fact, every single relation between intermediate values transform from standard program to zero-knowledge representation must be verified, and without any optimizations, it will be the comparable workload on both sides, on the sides of the prover and on the sides of the verifier, while for slightly increased workload, we can transform the workload from the verifier side to single and many verifiers. Many verifiers can decrease their workload at cost of slight increase of the workload on the prover side. Okay, so prover side sacrifices his computation for speeding up the computation on the verifier side. And typically, this means that with respect to number of constraints or relations on the which corresponds to given program, and by factor log n, the verifier can verify the proof in constant time or logarithmic time, which is quite fast. Of course, we cannot optimize everything, right? There are properties which matter, which are related to zero-knowledge proof systems like performance, prover speed, memory, proof size. Some systems need some transparent setup, and this is connected somehow with post-quantum safety and verifier cost. And also there is a triangle which says that there is some trade-off between expressiveness and developer user experience and efficiency of the development and implementation of zero-knowledge proof systems. And different priorities lead to different proof systems. So you have to really know what you want so you can choose the proper system to be used in your use case. Okay, so now a bit, this is mathematical slide, but I would like to try to explain it. Very simply, in general, zero-knowledge proof or digital signature can be viewed as a most simple zero-knowledge proof where we have a prover in the role of signer, we have a verifier with some public key, and we can change a bit the messages between prover and verifier, so it will become a standard pipeline of steps performed in zero-knowledge proof system. So first of all, there are two private values, nonce and private key, and one of these private key, one of these secret values are hidden, in fact, in some exponent, and the result is sent to verifier. And the zero-knowledge proof here works like challenge-response protocol, right? The message on the verifier side is challenge, where the prover compute the corresponding digital signature SR, and using some simple equation, and this is linear equation, so this simple equation based on the plus and addition and multiplication operation. So this relation is very simple, and since it contains secret values, it must be hidden or embedded in some hard mathematical problem. Okay? So every single zero-knowledge proof system consists of simple relations or variables which are defined by very simple operations, additions and multiplications. But since they are, some of them are secret, they must be hidden or embedded in some hard mathematical problems. So this means that this means increased workload on the prover side, right? Because you can compute the values, but you must hide them in some complex problems, and this needs some complex operations. So at the end, the signature is sent to verifier, where it can use some public values to verify the equality somehow. And here you can see that it contains, or it provides three properties of these systems: completeness, soundness, and zero knowledge, which means that it gives no information about the private key, in fact. Or without knowing the private key, the prover or signer, in the digital signature terms, cannot compute the valid digital signature for given message. Okay, and on the other hand, completeness means that honest verifier, prover can be verified correctly on the verified side. Okay, so generalization zero knowledge system to arbitrary program. In fact, we can look at it as a set of digital signatures for each specific linear equation. So each program is transformed into zero knowledge proof representation, which is just linear equations. Or from my point of view, it is just program which is transferred to linear equations, and all these equations must be verified somehow. So you can imagine that. So the model can be that every single equation is digitally signed, and the verifier must verify all these digital signatures. But this is, of course, highly inefficient, and there are ways how we can optimize the number of these signatures, number of these so-called constraints, and of course, in practice, we are using different systems not only to minimize number of constraints, the equations, but also to evaluate them efficiently in practice. Here you can see one example, by the way, that simple comparison age compared to some value is represented in the knowledge proof system by very complex equation which expands to many linear equations. So this is the reason why there is a significant overhead on the prover side, because standard program, I don't want to say explode, but definitely expands to many 100 times or 1,000 times more operations than the original program. Okay, here you can see the entire pipeline where we are, starting with some program. It's not working. Okay. Yeah, we are starting with some program, so everyone knows how the program works. Then it is transformed into symbolic circuit. Okay. On the atomic level, this is just sequence of linear equations of intermediate values, and maybe some additional variables is needed to add to represent more complex operation, which must be encoded this way. Then the prover substitutes the variables by actually real numbers, so the entire program is executed, and this will give the equations over real values. But these values partially depend on secret values, so you must hide them in some hard mathematical problems, either it is discrete logarithm or elliptic curve or I don't know, lattices. And next phase is commitment, but in modern zero knowledge proof systems, this is already done on the prover side using some tricks. And at the end, we verify, prover produces some compact proof which can be verified by anyone on the side of the verifier. So once again, from program to proof, this means that the program must be expanded to sequence of intermediate variables of the program or additional variables we need to encode to some not easily representable operations using operations we are using in zero knowledge proof systems. And this slide says about that at the beginning, or like 10 years back or 15 years back, there were two kinds of different families of zero knowledge proof systems. Some of them were based on hash functions like Starks, scalable, transparent argument of knowledge, and some of them were based on elliptic curve pairing systems. And these snarks, succinct non-interactive argument of knowledge, are very efficient because they produce very, very small proofs of arbitrary claim and provide some fast verification. But they need some, typically they need some setup. And since they are based on elliptic curves, they are not post-quantum resistant. On the other hand, Starks are based on hash functions, which means that they are post-quantum resistant and they do not need the trusted setup. On the other hand, the proofs for them are slightly bigger, so in the it's like logarithmic of n, where n is number of constraints produced by transcription of the code. And nowadays, we have already snarks which are also post-quantum, but they are not fully, okay, they cannot be used instead of, or are not optimized as Stark systems, the system from the Stark family. And that's the reason why still we are working with snarks and Starks. And typically, we are combining them into some hybrid combination where some computation, some program is, from this program, the Stark is applied and some larger, slightly larger proof is created. And we are using the snark on the top of that to decrease the size of the resulted proof, which allows very simple, efficient verification on the verifier side. Okay, this is a slide about how we decrease number of constraints, because I have already said that every single operation is transformed, is represented in zero knowledge proof systems using some linear equations or more complex equations. And we need to compress these numbers so that verifier is not, does not need to verify every single constraint produced by the prover. And the trick is that, in fact, we are using some interpolation of, let's say, constraints, and the verifier needs only to verify randomly selected point on this curve, which might mean that either some of the original constraints is verified, or some random which really corresponds to all of them. Okay, it is not so that we are selecting here the random point, and this point, when evaluated, gives us specific constraint from the prover side, but also here we are selecting some random point which is or depends on all possible constraints generated on the prover side. So this means that many constraints are compressed into proof that is much faster to verify, and that's the reason why verifier does not need to re-execute the entire program to verify the proof. And there are some advanced techniques where we can speed up the computation or minimize the number of constraints. And I think that I don't have time to cover all of this, but let's discuss two most important, batching and recursion. So this is a very nice trick, and maybe this can be applicable to your domain. So the trick is very simple. Here, the standard equation for elliptical DSA, which is just linear equation over the points and some scalars. So the problem is that the multiplication in ellipticals is very, very expensive compared to addition. So the trick is how to combine multiple digital signatures so only one single verification is needed. And the idea is to decrease number of multiplications. So it suffices just to put together the scalars, like hash of the messages here, or parts of the digital signatures Ri. And here you can see that on the right-hand side, we just use one single multiplication. And the same holds for parts of the signature, which means that now only one check is needed, and it uses only one multiplication on the right-hand side. The similar trick can be applied to the left-hand side. So, in fact, multiple digital signatures can be verified in one single verification. Okay, and maybe this trick can be also applicable to your domain. Okay, so there are two ways how we can transform the program to circuits, and we can use a skilled expert who will transform the program into minimal number of constraints, or you can use automated tool which will transform directly, automatically the constraints, the program into constraints, but of course there will be some prover overhead, and definitely the number of constraints will not be the minimal. Okay, so about few words about the future. Currently, or the community is working on hardware acceleration of some of the computations, and these typically include evaluation of the polynomials or hashing of the values, so things that happen at the early stages of the entire process. Then, very fast is moving zero-knowledge virtual machines, which prove the normal programs and transform it into constraints and proofs automatically. And there are some, of course, communities working on some tricks and arithmetization, where arithmetization is just transformation of the program into equations. And also, I have to say something about the zero-knowledge proof-friendly primitives. For instance, Poseidon is hash function, which is zero-knowledge friendly, which means that when translated into zero-knowledge proof system, it consists of, I don't know, 100, I think, constraints, while standard SHA-256 is expanded to 25,000, so it is like 250 times more. So definitely there are some primitives which are quite efficiently transferable to this domain. Okay, so improving slowly versus hard limits. So post-quantum systems are not moving so fast, but hence the primitives, if you want to encode these programs into post-quantum systems, it will take some time until this system will be faster, let's say. Also, the processing of program or transforming the program into zero-knowledge proof transcript or track, let's say, needs some memory, and there are some processes which can slightly decrease the need for this memory, but definitely this is not moving as fast as expected. And developer tooling and also audit is not moving, definitely not so fast. What are the hard limits? It should be noted here that on the prover side, he must embed the computation into some hard mathematical problem, so there will be always some overhead. Okay? Another overhead is that some standard programs must be expanded to many more, or 100 times or 1,000 times more constraints, and that definitely we cannot solve it completely. We can just apply some minimization techniques and combination techniques which will decrease, but definitely it will always be bigger compared to the original program. So it will be always more, the speed will be always slower compared to native execution of the program. So I think that's all from my side, and
thank you.
I hope that at least I give you some hints how zero-knowledge proof works. I don't know whether it was understandable, but we can discuss maybe.
No, you had all the important parts here, and again, I might have forgotten to say before, there will be recordings so that you can see the slides and the recordings later. Thank you very much, Marek.
Thank you.